Good morning. We will be now continuing our lecture on dynamic stability for longitudinal case. I was mentioning about this E, and E was given as G into mu Zu minus Z alpha mu Zu minus m alpha. It is m alpha Zu minus Z alpha mu. Remember, for theta 1 equal to 0. For theta 1 equal to 0. Now, let us try to extract some more information out of this E. What is the condition for dynamic stability? That E should be greater than 0, right? That is all A, B, C, D, E all should be greater than 0, and we are only studying the case E greater than 0 and see whether we are getting some meaningful additional information or not. That means m alpha Zu minus Z alpha mu greater than 0, is E greater than 0. That means m alpha by Z alpha greater than mu by Zu, right? Now, you substitute the expression of m alpha, Z alpha, mu and Zu, then you will get this expression as dCm by dCl equal less than Cmu by Clu plus 2 Cl1. I am sure you should be able to do it. You have to simply mechanically substitute the expression of m alpha, Z alpha, mu and Zu, and from there you can derive this. Please derive yourself. If you have some difficulty, you can go back to my last course on static stability and static stability of the aircraft. There also have derived this, but I am sure it does not take extra effort to do all these things. Now, let us see, once this is done, what is the meaning of this? What is dCm by dCl? Remember, dCm by dCl, the moment somebody utters dCm by dCl, we say dCm by dCl less than 0 is the condition for static stability, right? If you see here, again, this is Cm, pitching moment coefficient, this is Cl, and this is the line at trim. If this slope is negative, we say the aircraft is statically stable, because we know that if there is an increase in Cl because of disturbance, it will immediately generate negative pitching moment and alpha will be changed, right? So, it will go down. So, the Cl will again come back. So, it has initial tendency to come back. So, suppose Cl has increased, so the aircraft will automatically generate negative pitching moment. So, angular of attack will be reduced and the Cl will have a tendency to go back to the equilibrium Cl. So, we say dCm by dCl should be less than 0. Also, we have seen earlier dCm by dCl is approximately I can write as distance between neutral point and xCg of the airplane, the minus sign, right? And this is nothing but I can write minus as static margin or stability margin. This we know. But what does this say? It says if Cmu is 0, meaning thereby what? What do you mean Cmu is 0? That means where from I got this Cmu? Let us again go back. Cmu was m1 dCm by dm, and as we are going to a transonic to supersonic around that zone, the aerodynamic center of the tail will be moving far off. Even for wing also it moves, but tail having a large tail arm, so that will give a nose down moment, right? So, that will make the aircraft to pitch down like this, right? And that is why it is called tuck under. But for subsonic case, that while Cmu is 0, there are no shift in aerodynamic center of the wing or even the tail, right? So, for subsonic case, the condition still remain dCm by dCl less than 0, which will satisfy both static and dynamic stability. But if it is on the transonic or around towards supersonic, transonic, that region where CMU is not 0, what happens then? What is the information you get out of it? For transonic, on a case where AC of the tail or wing moves aft, right? So tail arm is there, so nose down moment comes, tuck under comes. We call tuck under phenomena. A lot of aircraft we used to lose because we could not identify this phenomena. So CMU, such case is not equal to 0. Then what happens? So let us take an example. Let's say CMU is minus 0.10, then your DCM by DCL, which is nothing but XCG minus neutral point. Okay. This should be less than minus 0.1, and CLU, what is the value of CLU we take? Let's say we say CLU plus 2CL1 is typically 1.0. Right? You can see that if I am flying with the CL 0.5, the 2 into 0.5 becomes 1. CL is very small, so it's not a bad approximation to take this value as 1.0. So I put it as 1.0. So this becomes, it should be less than minus 0.1. So what is the message you are getting now? It's saying if you want to ensure both static and dynamic stability for such case where it's going for transonic, then DCM by DCL should be less than minus 0.1. Just being less than 0 is not sufficient. Right? Okay. For a specific case, for a case where I have assumed these values, right? So important thing is it is not sufficient just to have DCM by DCL less than 0. That means if you are not aware of this condition and you think your neutral point is here, CG is here, and this is the airplane fuselage reference, and you think neutral point is behind CG, so the aircraft will be dynamically stable, but this says, no man, that's not true. You have to ensure that this separation is validated through this condition, because DCM by DCL is nothing but distance between XCG minus NP. But that is the understanding. Okay? That connects static stability to dynamic stability. Right? Clear? Okay. Let us try to handle this characteristic equation. Let us say for an aircraft, the ABC values are like this. A is equal to 675.9, B equal to 1371, C equal to 5459, D equal to 86.30, and E equal to 44.78. Right? You can immediately check, applying Routh criteria, that both the conditions are satisfied. One is that all the coefficients are greater than 0, then the condition of D into BC minus AD minus B square E greater than 0, you can check both these conditions are satisfied. Right? But what we want to find out now is the roots of this equation. And if you apply numerical methods, you will find it will generate roots like this. Lambda 1, 2 as minus 1.008 plus minus 2.561 j, and lambda 3, 4 as minus 0.069 plus minus 0.0905 j. Now let us again come back here. This is, we are expecting 4 roots. You see 2 plus 2, 4 roots are there, right? Now, we have seen A, B, C, D, E greater than 0, and also second condition is also satisfied. So, it will be having roots which will lead to dynamic stability, no instability. That means, no real part of this root will be positive. That comes from those conditions. And now, what is important to see here, that this pair of roots, the real part, if I plot, it is imaginary, it is real. So, it is, let us say, minus somewhere here, right? Minus 1.008, and these values are 2.56 plus minus. But the other one is somewhere here, right? That is minus 0.0069. Now, can you tell me which one will belong to short period? That means, what is short period? That if slight disturbance is given, then the airplane will excite like this and come back to this equilibrium within a very short time, so short period. And within this short period, we can fairly assume that the u remain constant. Okay, there is a change in the speed. So, that is short period, and that is phugoid like this, right. For short period, the real root has to be relatively large, negative. So, this belongs to short period, and this belongs to phugoid. Now, you are expert. If I try to ask you what will be omega n short period, zeta short period, you should be able to find out. Yes or no? You have done it so many times. Now, it is only second order equation you are handling. If I pick this lambda 1, 2, the method will be very simple. I will construct the equation as x square minus sum of the roots, that is minus 1.008 minus 1.008, sum of the root into s, plus product of the root will be minus, will be 1.008 square plus 2.56 square. Okay? So, now, I will compare this with s square plus 2 zeta omega ns plus omega n square equal to 0, and I can find out the value of zeta and omega n as zeta sp means short period will come out to be 0.355, omega n short period will come out to be 2.836 radian per second. Right? Now, you could see that although AS4, BSQ, CS square, whatnot equal to 0, but finally, whatever we learned in the second order system, we are applying that as far as longitudinal dynamics is concerned. So, that is why we are spending so much time on second order system. Now, if you take the second pair of root lambda 3 and 4, if you do a similar exercise, you will find omega n phugoid as 0.91 radian per second, and zeta phugoid you will get as 0.076. So, you could see physically also short period is this. So, larger omega in short period 2.836, and phugoid is having motion like this, right. So, omega n is very, very small. The damping for short period is large, because immediately it comes out short period, during very short period it comes back to equilibrium. So, it is 0.355, phugoid it takes time, long period. So, it is also called phugoid or long period, right. So, it takes time to come back to the initial equilibrium or steady state, right. So, now you could see that although we wrote so many equations, finally, we are handling this such a simplistic way, because please understand, finally you want to design an aircraft. If you have to solve so many big equation, when is the time for designing the aircraft? So, smart man or smart generation will evolve such approximate way of handling things, and you can quickly see how to find out the natural frequency, damping ratio, so many other characteristics you will find, and accordingly you can design the aircraft. Okay. Whatever routes we are getting here through AS4, BS cube, CS square plus DS plus E equal to 0, we will call them exact routes, because they have been obtained by, these have been obtained by solving this exact equation. Right. Next step we will come to approximate equations, okay, and from there we will get again the meaning of short period and Fugard mode through approximation. That will be simpler. Okay. And finally, we will compare them with the pure pitch solution. Remember these three things, because as we will be evolving this longitudinal dynamics, at the end I must try to tell the designer, okay, hold on for this solving this exact equation, because you do not know exact value of A, B, C, D, E, because your configuration is not finalized. Don't worry, you start trying the approximate method to find the zeta and omega n, and still if you find no, you are not ready, use the pure pitch solution, right? And or once pure pitch, then upgrade yourself like this. So how to handle this, that will be my next part of lecture, which will have more of design influence. We'll now jettison out all this expression, etc., big equation and all. We have to come back to the aircraft, because finally we have taken oath, we are grooming ourselves to make sure we have correct physical field to design an aircraft rather than lost in big equations. Thank you very much.